Hi. So I'd like to get started with our first online lecture on the material, the course material. So this is just an introduction to nanoscience and nanotechnology. So to understand nanoscience and nanotechnology and what it is, you kind of have to understand the length scales that we're talking about. So nanoscience deals with phenomena that occur on the order of a nanometer, which is 10 to the minus 9 meters. There's about 1 billion nanometers in a meter. Okay, and the word nano comes from the Greek word nanos, which means dwarf or little old man. So this kind of reminds me of my big fat Greek wedding. Give me a word, any word, and I'll show you how the root of that word is Greek, right? Well, in this case, it actually is. So to give you kind of a sense of scale, I'd like to talk a little bit about what some of the powers of 10 mean. Changing by a factor of 10 or 100 drastically changes the physics that govern what's going on at that length scale. So let's look at this for just a second. Let's start down here at the nanometer. Now, a nanometer is about the width of a DNA molecule. Atoms are smaller than that by a factor of 10 or so for the most part. So you're dealing with things that are on the order of the width of a DNA molecule. Now, if you lined up 100 DNA molecules side by side, then you'd have something on the order of the wavelength of light. Okay, so the wavelength of light ranges from about 400 to 700 nanometers. So the things that we're talking about are about 100 times smaller than the wavelength of light, which is kind of mind-boggling. If you go 100 times larger than that, then you're getting into the world of your red blood cell, okay? Now, remember that quantum mechanics governs things that are on the order of the size of a nanometer or so. So once you get into micrometers, 10 to the minus 6 meters or so, you're talking about physics that can be applied to big things, me, you. Okay, so the physics is the same roughly for a red blood cell as it is for me and you. But quantum mechanics starts to kick in on the order of a nanometer. And that, of course, is a really fun region of physics to talk about. Now, if you go 100 red blood cells, now you're on the order of the size of the head of a pin. Okay, so about the width of a head of a pin. And then 100 heads of the pin will get you a Twinkie. All right, the length of a Twinkie. And then 100 Twinkies lined up end to end, and you'll have a school bus. And then 100 school buses lined up end to end, and you'll have roughly a 5K race, which is about the distance that a person can run in a half hour or so. However, 100 times that is about the size of the length of our state, North Carolina. And then 100 North Carolina lengths will get you the diameter of the Earth or so. 100 Earths will get you the sun. 100 suns will get you the distance between the Earth and the sun. And then 100 of that will give you the size of our solar system. 100 of those or so will give you a light year. 100 light years or so will give you a nebula. And then 100 of those will give you the size of our galaxy. And so there you have it, 28 orders of magnitude for your viewing pleasure, giving you kind of the idea of how powerful a factor of 10 can be, really, and kind of helping you understand why we need the scientific notation so drastically to explain some of these vast differences in distance that we're talking about here. Now, the government line, nanotechnology has become nanoscience and nanotechnology has become a government initiative, something that they wanted to pump a lot of money into because they see the commercial possibilities. So there's government bodies. One of them is the National Science and Technology Council, and they've defined nanoscience as the research and technology development in the length scale of approximately 1 to 100 nanometer range to provide a fundamental understanding of phenomena and materials at the nanoscale, and to create and use structures, devices, and systems that have novel properties because of their small size. All right. Now you can find out a lot of interesting information about what's going on in research in nanotechnology and nanoscience, and how the government kind of feels about nanotechnology and nanoscience at the website nano.gov, which is the website of the National Nanotechnology Initiative, which our government launched to help fund research in this important work. Now, nanotechnology, the definition of nanotechnology, is basically the application of nanoscience, okay? And so your textbook defines nanotechnology as nanotechnology based on the manipulation, control, and integration of atoms and molecules to form materials, structures, components, devices, and systems at the nanoscale. And it's the application of nanoscience, especially to industrial and commercial objectives. All right? So that's nanoscience and nanotechnology. Now, it's a difficult field to study in a sort of traditional framework. And the reason is that nanoscience and nanotechnology are interdisciplinary. So it really takes teams of people working together with different scientific backgrounds to come up with new innovations and work in nanoscience and nanotechnology. So let's go over some of the key players in that and sort of discuss their roles in this important research. So you have your physicist. And physics describes the properties and phenomena that the nanomaterials exhibit. So here you can see some quantum dots. This is an image that I've taken from Sigma Aldrich, and it shows the photoluminescence of these quantum dots. And they tune the composition between the cadmium, the sulfur, selenium, and zinc. They tune the percentage composition, and then that changes the color that the particles emit in the presence of UV light. So that's kind of fun. Chemists, they're concerned with the synthesis of the nanomaterials primarily and how they can modify them by chemical methods to exhibit different properties. And so here you can see some scanning electron microscopy images of these smart gels that are made of these high molecular weight polymers. It's a little tough to see maybe in this, but the scale bar here is on the order of, say, a micrometer, 1,000 nanometers, or hundreds of nanometers, depending on the picture. So you can see that these things have structure that's very rich on the nanoscale. The biologists are also very intricately involved. In fact, the biologists will tell you that they've been doing nanoscience for longer than anybody else because a lot of the processes that occur within our bodies and cells involve little nanoscale machines. So the biologists are concerned with describing and understanding natural nanomaterials and the integration of man-made nanomaterials into organisms, particularly in medicine. That's a very hot area of research in nanoscience and nanotechnology, for example. So here's a fun example of an application of nanoscience, the home pregnancy test. It often contains gold nanoparticles that are coated with an antibody, and these particles then bind to a hormone that's present in a pregnant woman's urine called HCG, and then it moves up the test strip and aggregates on the indicator line. So this image was taken from Discover magazine, and if you ever have the occasion to be involved in the use of one of these devices, you can thank nanotechnology for the quick rapid response time of the test. The engineers are also very involved, and these engineers could be chemical engineers, they could be mechanical engineers, they could be material science engineering. But anyway, their main objective is to understand the nanoscience and then apply it to the design of devices, circuits, and structures to solve specific problems. So, for example, there have been a lot of advances in nanoscience and nanotechnology that have been spurred on by the information age and the miniaturization of components for computers, cell phones, and things like that. This example right here kind of shows you how important it is. It shows a little tiny transceiver chip that's integrated into a circuit, and it fits on this guy's finger. Okay, so even 50 years ago this would have been inconceivable, and so advances in technology have made our information age possible. Nanoscience and nanotechnology are convergent technologies. They're horizontally enabling, and they cut across all vertical industry sectors. And nanoscience is a horizontally integrating interdisciplinary science that cuts across all vertical science and engineering disciplines. So, in other words, it's very interdisciplinary, and it requires the work of teams of people that have different areas and regions of knowledge. And the applications of that technology also can span across different disciplines. So, well, why nano? Why would you want to go nano? What would nano provide that macro scale or even micro scale devices couldn't provide? Well, basically, nanoscale materials have different properties than their bulk counterparts. And the reason, of course, is quantum mechanics. You're starting to get into the area where quantum mechanics really rules the day, and that can give you some really fascinating and interesting properties that you wouldn't see in the bulk of sample of that material, for example. These new properties then enable new applications which people really want to take advantage of. And we're going to talk a lot more about this in this class. So I'm just going to say that very briefly, at the nanometer scale, properties become size dependent. So for example, nanoscale materials are often more chemically reactive. And the reason for that, if you might know this if you've studied any chemistry, is the surface area to volume ratio. A good catalyst, something that spurs on and speeds up a chemical reaction, has a large surface area to volume ratio. And as you shrink a particle down, the surface area to volume ratio goes way up, and that makes them a better catalyst, more chemically reactive. They also have different thermal properties than the bulk materials, such as their melting temperature, okay? So the melting temperature can drastically change as you change the size of the particle, even if you don't change the composition. It can change the optical properties, such as the color or the transparency, and those are going to be different at the nanoscale than the bulk. So for an example of this is also an image from Sigma Aldrich. These vials contain a solution with nanoparticles in it, and as you change the size of the nanoparticle without changing the composition at all, the color of that solution changes. So you can see here you've got sort of an orange color for 30 nanometer particles, but as you go up to 100 nanometer particles, the color changes more towards purple. So that's kind of fascinating. Also, electrical and magnetic properties are different from nanoscale materials. The conductivity changes, the magnetization changes as you change the size of the particle, and you might want to harness that effect. Okay, so that's a nice little introduction. Below our introductory lecture, I've also posted some things for reading. I want you to read Feynman's lecture. There's plenty of room at the bottom, and view the fun video that talks about some of the size scales that we're working on below that. All right, so see you soon.